right, so okay, so let's talk about that one. Not gonna do that one yet. That one, that's right. We talked about the inscribed rectangles, right? Number 19. Did we do that one? Sample one. Sample one. We did 19. That one. We do 27. Okay, let's talk about that one here. So the average value of this function on the closed interval -4 to 0 is. So what are we going to do there? Integral of cosine 1/2 x, -4 to 0. Divided by what? B minus A, right? B minus A. So the antiderivative of cosine is sine. It is pretty bad. I'm glad you didn't try to speed, risk your life.
Why look the closest side of my here? That doesn't mean I'll wake up.
All right. Anyway, antiderivative is sine, and then you kick out a
2.
All right. So you put in a 0, that'd be 0. Put in a -4 times 1/2 would be sine -2. Right? Oh yeah, there's a 2 on that. So it'd be -1/2 sine -2.
How do you know to put it over the 0 minus?
Because I memorized the average value of a function is. You just got to memorize that for me. Average value of a function. Average value of a function is that value.
You're
Right. So yeah. Oh, that's unfortunate. That answer's not open. What I do? We talked about this. I'm pretty sure we did one like this the other day. Maybe it was in the other class.
usually move on. Go on. Oh, those are the X values.
My answer's right. Well, T. Why? This is a good guess. Some people would get that right. They'd say, oh, those two negatives cancel each other out. It must be E. But that would be wrong reasoning, but you get lucky. Oh, I guess maybe we did talk about this in the other class. It was, or in this class. It was the other class. Because this came up in one of the other packets. So either you guys didn't do that one, or you missed it, or I don't know what, or you just haven't asked about it because this same thing came up in another problem. And maybe it was this problem, actually. Maybe it was this problem they asked about. You guys did. I don't know. Even and odd functions. Even and odd functions is what this has to be. Okay. What kind of function is sine? That's even function. Odd functions, you put opposites in, get opposites out. So in an odd function, which sine is an odd function, it means if you put a negative x in, you get, it's the same as getting the opposite out. So this is, sine negative 2 is the same as negative sine 2, which would cancel this negative, and you get that. If this would have been negative 1/2 cosine negative 2, kind of function is cosine? Even function. So cosine negative 2 is exactly the same as cosine 2. So in that case, it would have been, so if sine was an even function, then it would have been a. Sine negative 2 would be the same as sine 2, because that's the way cosine is. So again, remember, in the multiple choice section, this is where they really make sure you know all those kind of pre-calc rules. Even odd functions, your logs, your exponentials, your trig values, all that pre-calculus stuff. And that's one right there, even odd functions. Okay? We did this one. I know we talked about that. That was a sigma kind of thing. Then we got a volume problem, which we can't do. We talked about this average rate of change. Or no, I don't think we did. I think somebody asked about that. Trapezoid rule, I think we talked about that one. See, trapezoid rule now. Trapezoid rule, you know, what I would do is what we learned yesterday, the new way of doing the trapezoid rules. 10 minus 0 divided by, and you're doing how many subdivisions? You have 10 subdivisions there. So it's 2 times n, 2 times 10, and then we do what? We do 1 of, yeah, so it'd be f of 0, right? I mean, I don't know if I need to write that out. F of 0, which would be 20, plus 2 times 19.5, plus 2 times 18, plus 2 times 15.5, right? Plus dot, dot, dot. Now, this is calculator one, so you can just go right on your calculator. So you're going to do that, 2 of those, 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 and then 1 of those, right? And you're going to multiply that by that, right? B minus A, so the formula we had yesterday, B minus A over 2n, and then your trapezoid rule. So when it says a trapezoid rule, do that. Now, if you'd rather write out all the trapezoids, if you'd rather go 1/2 times and then 20 plus 19.5, right, times the width of 1, that would be your first trapezoid, right? Your second trapezoid would be right there. 1/2, 19.5 plus 18 times 1. I mean, if you'd rather write that out and do it that way, that's fine. I don't care, right? That shows you understand what's going on, right? I got 10 trapezoids. That's fine. But we said, hey, we can pull out the 1/2. We can pull out the 1. That's what this is. That's the B minus A over 2n. And then we can just add up 1 of those, and then 2 of those, and then 2 of those. Okay? So that's connected to what we were just talking about here, trapezoid. Okay? All right, here's another example, 33. There's some stuff we've been talking about. Let R represent the rate at which water is leaking out of a tank, where T is measured in hours. Which of the following expressions represents the total amount of water in gallons that leaks out in the first 3 hours? R is water. So what are the units of big R? Gallons per hour. Those are the units on big R. The rate at which the water is leaking out, T is measured in hours. And then gallons is your amount of water. What's the total amount of water that leaks out in the first 3 hours? Because this would be gallons per hour. The DT would be hours, gallons per hour times hour. Now we said that was net, but it's leaking out. We're going to make that assumption that it's. Remember we said as long as it's going one direction, right? As long as the car is going one direction, the net distance is the same as the total distance. So therefore, it'd be the same thing here. We got water leaking out. So the net amount of change in those 3 hours is going to be the same as the total amount of change in those 3 hours. Okay? So it's just a matter of understanding. This would be an average value kind of thing. This would be gallons per hour. The antiderivative then would be gallons per hour. So the units on this would be gallons per hour. This would be gallons, but then divided by 3. This would also be gallons per hour. This would be the average of R. So that'd be the average rate that it's leaking out. That's not what they wanted. Okay, this would be gallons per hour up here, divided by hours. So that's gallons per hour, so that's no good. And then this would just be gallons per hour, right? I mean, so you can just look at the units and you can tell what these various things are, okay? So, hopefully that's, pretty easy question. Okay, area of a region we haven't really been into. Let's talk about this one. Table for acceleration of a particle from 0 to 8 is given in the table above. If the velocity at t equals 0 is 4 feet per second, the approximate value of the velocity in feet per second at 8, computed using the Riemann sum with 4 subdivisions of equal length, is. Okay, so let's break that apart a little bit. This is acceleration, feet per second squared, from 0 to 8. Nice even interval. The velocity at t sub 0 is 4. So what I would do is I would write that this way. Okay? Now, what's another name for v? Well, what's another name for a actually would be better. Couldn't we label this row here v prime? I think it's good to get the same units or the same names into these problems. I would call that v prime. So the approximate value of the velocity in feet per second at 8, so they're wanting v sub 8. They're wanting that, right? So tell me what I can do with v sub 0, v sub 8, and I've got v prime. And what do we use a Riemann sum for? Find an area, or it's another word for it. Starts with an I. We use a Riemann sum to approximate at a what? An integral. An integral. Right, area, but I mean, we use but we're talking about how an integral can mean more than just area, right? We use a Riemann sum to approximate an integral. I said this the other day. People get confused when they read a problem that says, hey, find, like in this problem, find the velocity using a Riemann sum. You're like, how can I do a velocity finding a Riemann sum? You're not finding a velocity using a Riemann sum. You're going to find an integral using a Riemann sum. So what do we need to set up here? An integral. See, that's the thought process you need to have here. When you read this problem, that's why I did this with the units. That's why I have the v prime there. That's why I got those v's there, right? Is I put those in there because when I saw the term, when I saw Riemann sum, I immediately thought of an integral. I need an integral. That's what I use a Riemann sum for. So tell me what I could set up. The integral from 0 to 8 of v prime would equal v of what? V of 8. Remember that problem yesterday? Remember that problem yesterday that we set up like this? Because we could do this. Remember that was the one that Jesse asked about? We couldn't do the antiderivative. It kept spitting it back at you. Right? You couldn't do the antiderivative. But we could do this on our calculator yesterday. Remember that? And then they told us, didn't they just tell us this one? They told us v of 0. So doesn't that leave us this one we can find, right? So they told us this. Now, how are we going to do this? The Riemann sum. So we're going to do this side with our Riemann sum. Okay? And they didn't tell us what kind of Riemann sum, though, did they? That's interesting. what would they usually tell us? Right, left, midpoint. Okay, now they said 4 subdivisions. So could we do a midpoint? We don't have enough points to do a midpoint. Okay? So do we have to just guess? Do we do a left or right? Well, let's say we were going to do a left. What numbers would we use? Well, because 1 subdivision, 2 subdivisions, 3 subdivisions, 4 subdivisions. So what would be your midpoint? Yeah, but what's the y value? You don't know the y value in between, right? You'd have to do 2 subdivisions to do a midpoint, then you'd have this point. So let's say we were going to do a left. Which points would we use? Those are the x values, but that's we use f of 0, f of 2, right? So we would use 2, 3, 4, and 3. If we're going to do a right, we would do 3, 4, 3, and it's the same. The left would leave off this 2, the right would leave off this 2. So they purposely did that, which was kind of confusing, but so it doesn't matter. So let's do a right. Okay, so a right would be, so what would we do? Let's do it with our new way of doing a right Riemann sum. B minus A over N times f of, we're doing a right, so that'd be f of 2, so that'd be 3 plus 4 plus 3 plus 2. See how this can be a little easier instead of writing out 4 rectangles? I liked it before when we did height times width, height times width, height times width, because it made you think of rectangles. But I think we're past that now. I think we know Riemann sum means rectangles, sigma notation means rectangles. We did all that. Now I think this way is better. I don't care. If you want to write height times width, height times width, height times width, that's fine. But this is b minus a over n, f of 2, f of 3, f of 4, or excuse me, f of 2, f of 4, f of 6, f of 8. Okay, what do we get there? 7, 10, 12 times 2, we get 24. So we use the Riemann sum to do this side over here. Equals v sub 8 minus, and what was v sub 0? 4. Add 4 over to there. We get v sub 8 equals 20. Really important stuff in that problem that I've been talking about here this week is when it talks about use a Riemann sum to find v of 8, we're not using a Riemann sum to find v of 8. We're using a Riemann sum to find an integral, right? But we had to write out this equation using our integral. We had to build an integral, okay? And again, that's some stuff I've been talking about the last few days. We had to build an integral first. And then, how are we going to find this integral? Well, if they give me an equation for v prime, maybe I can just go to my calculator. That's what we did yesterday. Just went to our calculator. If it's an equation where I can do an antiderivative, and this is a no calculator problem, maybe I do my antiderivative here, fundamental theorem part 2. Or, oh, they gave me a table of atoms. Okay, well, I'll do a Riemann sum to approximate that. Okay, all right. Quickly here, let's... You guys set it up. This is the calculator section. It is. So, like the one Jesse asked about, isn't this just like the one Jesse asked about yesterday? You got F right here. It says G is an antiderivative. They give you G of 5, then they want G of 1. So your thought, and Scott, I don't know if you had a chance to see the video, but Jesse asked about one of these yesterday. So your first thought on the calculator would be try to find the antiderivative of that, right? G is an antiderivative of F. This is F, so we try to do the antiderivative. Guess what? There isn't one, right? There isn't one. There is no antiderivative. If there was, that'd be great. You'd have a plus C, you'd plug in your initial condition, find the C, then plug in a 1, and you'd have it. So that's a great strategy. Sometimes that works. So you don't want to, not think about it, but sometimes that works. Well, turns out we're not going to do that, right? And so what's another name for F? G prime, right? So G is an antiderivative of F, so that means G prime is F. So if we do the integral of G prime from 1 to 5, that would equal G of 5 minus G of 1. And they told us G of 5 was 7. And then what do you get on this on your calculator? This one right here, 10.882. So add this over here, so it's going to be G of 1 is equal to 7 minus 10.882, which I'm guessing is, that doesn't seem right. Did you say negative? No. Is that right? 7 minus that is, oh yeah, that's right. Yeah, that's negative. Yeah, 7 minus 10.82 would be negative 3.82. Right. So there you go. Okay, yes, that's exactly what we're just doing. Okay, enough of that. Pounding it into your head. I'm hoping you guys are hard-headed. I don't know. I'm hoping it'll stick. Okay, so a lot of this same stuff. All right, so were you able to log in? Only one person is logged in. Yeah. Who's that? Max. Max is presenting. So let's move along here and let's get your homework out. Let me take a quick look at that. Oh, get out that 2016 packet too. I want to look at the other part of that. Okay. 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 Yeah. Okay.
Yeah. What do you have for the C?
That's fine. So on the page. Yeah. Yes, sir.
I need 3 halves and 3 1/2.
Yeah, so it's assignment sheet. You get that assignment sheet. Well, it was on the website, but it's assignment. It was at the top. Okay. Oh, yeah. Yeah, we'll talk about 52. All right, maybe just quickly mention, was any problem on that 2016 packet? What happened with that? Okay, lost it. Okay, get back. Okay, there's number 6. So we were talking here about this. So this is just a quotient rule. But what about this? So the antiderivative of f double prime is 1/2 f prime of 2x, right, from 1 to 3. So it'd be 1/2 f prime of 6 minus 1/2 f prime of 2, right? And then you just read them right off there. So f prime of 6 is 5, so that'd be 5/2. And then f prime of 2 would be -2 times -1/2 would be +1. You do that right? 7/2. Okay. So just again, that same kind of thing we've been talking about with the fundamental theorem part 2 and all that, and using a table of values. So it was interesting. This was a lot of teachers squawked about this one after the AP test. I'm on the a group email whatever thing with other AP teacher. Well, it's just the AP, the college board, the people who do the AP, they have these different discussion boards for all the different subject areas, so you subscribe to it. But anyway, and so people post questions and say, hey, I'm teaching this, or any ideas, or I came up with this question, whatever, that kind of stuff. So after the AP test, there's always a lot of discussions. Once they post these free response questions, there's a lot of discussion about, what'd you get for this? What are the answers? Oh, this one, my students really. But that's what they like about our book. Our book does these kind of problems. Well, right from the beginning when we did change, a lot of books don't do this. Now they're starting to, because now the AP is starting to put these on there and make you think about them in a little different ways, especially with tables of values. So I think we've always done pretty well on those. But it was the type of problem they had to put. It's a type. We've seen this in our book, right? We've seen these tables like this and asked these questions quite a bit. Clear back to when we first learned derivatives, and so this didn't bother us, students. But it was unusual when I saw it on the AP test. I was like, oh, well, they haven't had that on there in a while, or forever maybe. All right, so let's move along. So yesterday we were talking about this. Just a quick summary here from yesterday. We were talking about how lefts, if the function is increasing, lefts are going to be under, rights are going to be over. If the function's decreasing, then lefts are going to be over, rights are going to be under. So we just got to understand that part of it. And then the steeper it is, we said, right, the steeper it is, the more a rectangle will be off, because a rectangle assumes the graph stays horizontal when most of the time they don't. So the farther it is away from horizontal, the more error there's going to be. Trapezoids, of course, assume that the graph stays linear, but the more it curves, and we didn't talk about that yesterday, but the more it curves, the more error there's going to be. Well, what do you suppose measures curviness? I mean, if the derivative measures the steepness, the slope, right? Like f prime of 4 is more than f prime of 2, right? Steeper. So there's going to be more error. Well, what measures the amount of concavity? F double prime. Now, I've never talked about that, but what if f double prime is 4 versus f double prime being 2? Well, it's more what? It's more concave, right? I mean, that's right. I mean, we've never really talked about that, but a second derivative of 4 at a point compared to a second derivative of 2 means that the graph is not only concave up, but it's more concave up. So it curves more. Okay, so the more it curves, the more error there will be on a trapezoid or on a midpoint. Okay, so the second derivative is going to be involved in how much error there is on these. Okay, so anyway, and then the other thing, Skyler, is that we said a midpoint rectangle. A midpoint rectangle can be thought of as a pivoted. See, here'd be a midpoint rectangle right here. Well, that would have the same area as if you took that top line and pivoted it and turned it into a trapezoid. But it's going to be tangent to the curve because it's going to touch right there at the pivot point. So a midpoint rectangle will be below this curve, whereas a trapezoid would be above. Okay, so that's over and under approximations. All right, and then these are the different things that we wrote out yesterday, and then we had this new one called Simpson's rule. Okay, and those are the long versions, and then yesterday we said a trapezoid can be thought of as just an average of a left and a right, and then we said Simpson's rule is just this. I wouldn't worry too much about this 2n. Just remember that if you're doing an S8, you're going to use an M4 and a T4 there in those formulas, right? You're always going to use half. Matter of fact, we could have had this be SN and then this be half N. That just seems weird to do, so they don't do that. But so don't worry too much about, some people get hung up on this isn't 2N and this is. Don't worry about that. Just worry about Simpsons always has to be even. And if you're going to do the shortcut, the average formula, then you do S8 here, you'll have 4s there. That's all you got to remember. Okay, if you're doing an S8, that means you're going to have 9 items here, and N is going to be 8. So don't worry about that, 2N business. That's not really a factor. Okay, all right. So we had those things, and then we talked about this right here. Now, let's go ahead. You might jot this down because this is probably going to the next level here, and I don't know if any of the homework problems really touch on this, but it's probably what we're going to talk about here a little bit today. And that is, well, matter of fact, before we do that, before we do that, let's talk about the homework. So I know we got to talk about 51. What else? 14? So 14 says, so I is equal to the integral from 5 to 7 of cosine x dx. Write out the approximating sum S4. Okay. So 7 minus 5 over 3 times 4 be f of, so we do the same thing we've always done. We go 5 to 7. We're going to do how many subdivisions? 4. So what will that be? That would be 5.5, 6, 6.5, and 7. So we would want f of 5 plus 4, f of 5.5 plus 2, f of 6 plus 4, f of 6.5. I don't know if I'm answering your question here, Emily.
Yeah, I wasn't sure. So then was the last one just F of?
Right. So on Simpsons, it's always the first, just like trapezoid, the first and the last, there's just one, right? And it goes to the left and the right edge, right? We said there's always n plus 1 items in there. So if you're doing an S4, there should be 1, 2, 3, 4, 5 items in there, right? And it does that 4, 2, 4 pattern, right? And now you just take those and plug those into cosine and just use your calculator, to do it, okay? And then it says compute the approximation error made by that. Well, how are you going to do that, part B?
You just find the definite.
Yeah, it's just I, the exact answer, minus S4. That's the approximation error, okay? The amount of error, that's what we talked about. So find the exact answer. So the antiderivative of cosine, you can do it under calculator too, but the antiderivative of cosine is what? Sine. So it'd be sine 7 minus sine 5.
You're not at 0 there. Alright, that's 4
Okay, Max, you're the presenter. Show us. Okay, so do the integral first. Do the integral of cosine from 5 to 7. Okay. Now I would change your settings. You're only showing 6 decimal or 6 places. You're on float 6 on that. Go to doc and, or is it menu? No, right there, doc settings. Document settings. Yeah, change that float to just plain old float. So then you get like 12 decimal places. Enter. Hit control enter again. Then you get to your control enter. There you go. Okay, now okay, so then it'd be, what do we have? We had, what do we have? 1/6 out in front, was it? So we'll divide by 6 at the end here. So just do cosine of 5. Cosine 5 plus 4 cosine 5.5 plus 2 cosine 6 plus 4 cosine 6.5 plus cosine 7. Control enter. Divide by 6. Yeah, so arrow back up, what was your other one? 616, see, so it's different, but it's close. But it's, and you didn't have maybe enough decimal place, but it's, so now now grab that one, minus that one, right? And so it'd be, and the absolute value bars, so we ignore that negative, so it'd be, so the approximation negative 0.000578, maybe, or whatever. Is that what you guys said? But it'd be positive, yeah. Okay, so that'd be the approximate, that'd be the amount of error. So not very much. So that tells us that Simpson's method, when you see these zeros here, Simpson's method was accurate out to 3 decimal places. Right? It's kind of what we did with Newton's method. Remember, we talked about how many zeros was kind of how many decimal places of accuracy we had. So with just 4 subdivisions, we had pretty good accuracy with Simpson's rule. So that's good to know. Okay, Simpson's rule is going to be fairly accurate. Okay, what else? $51 for sure. Okay. What about on like number 3? The integral 0 to 1 sine of x squared dx. Why is it true that L7 is less than or equal to I is less than or equal to R4? This graph from 0 to 1 is increasing the whole time, right? And that's all you need, really, right? Sometimes I get people that calculate out L7, calculate out R4. It'd be okay if you did, but you really didn't have to, right? It's L7 is less than, is an under approximation because it's increasing. R4 is an over approximation, so it has to be. And it doesn't really matter what the 7 and the 4 are. Doesn't matter. 1,000 left rectangles are going to be an under approximation. You know, and 2 right rectangles are going to be an over approximation. It doesn't matter, okay, as far as over and under. Okay, so 51, that's it. So the whole section there, what did you do, 29 through 34? You're all good with those. It just had to do with increasing and positive, right? So trapezoid, so if you have a midpoint, you don't really know, right? So like on 30, is a midpoint less than the integral? Is a midpoint an under approximation of that? We don't know. It depends on what? It depends on the concavity, right? So just because it's increasing, we don't know. A midpoint would be an over approximation here, right?
It says it's concave down.
Where? Not on 30.
Oh, wait, yeah.
Does it say that it's always increasing?
It says positive and increasing over the integral.
So what did that mean? Concave up?
No. Oops. Oops. There you go. That's concave down. That's increasing and concave down. So a midpoint.
I guess I thought it meant like the slopes were always increasing.
No. If it meant the slopes are increasing, it would have said the slopes are increasing, right? It says the graph is increasing. The graph's going up. Increasing is different than concave up. Okay? So here's a graph that's increasing. The midpoints would be under. Remember, the midpoints are a pivoted trapezoid. Midpoints are a pivoted trapezoid. So they're tangent. So here, the midpoint would be under. This graph is increasing. Here, the midpoint is over. The pivoted trapezoid is over. So here's an increasing graph where midpoints are under. Here's an increasing graph where the midpoints are over. Right? So, right, it's increasing is not the same as concave up. And concave up or concave down is not the same as increasing. Here's a graph that's concave down. Part of it's increasing, part of it's decreasing, right? But it's concave down. So concave up, concave down, totally different from increasing, decreasing. Okay. You're going to get to do some more of those here in today's time. So in that section, the only ones you knew is you knew lefts were going to be under and you knew rights were going to be over. So when it says 29, is left less than? If it's increasing, yes, left will be increasing. Must be true. M might be true. We don't know. Is L less than R? 31. Well, yeah, yes, must be. What about 32? Is L less than M? you know the graph is increasing, okay, here's two examples. What's a left going to be? Under. Left's going to be under, for sure, right? Left's going to be under. What's a midpoint going to be? Could be under, could be over. Well, what if it's over? Then the left is definitely less than the midpoint, right? What if the left and the midpoint are both under? So the left's going to be more under, right? Because the left is going to be here, right? The midpoint's going to be a better approximation. Midpoint and trapezoid are always better approximations than lefts and rights. So if the left is under and the midpoint's under, which one's under more? The left is under more. So is the left going to be less than a midpoint? Yes. Yes.
So 33 and all, the left is also less than the
So 33, is the left going to be less than the trapezoid? Trapezoid's the same thing, just opposite, right? Trapezoids, let me put the trapezoids in red. If you had this situation, the trapezoid would be here, right? That'd be the trapezoid, it'd be over. Here'd be the trapezoid in red on that one, concave down, it'd be under, right? But no matter what, the left is going to be more under than the red trapezoid will be. And the left is definitely less than this one, because here it's an over approximation. So yes, so 33 must be true. Must be true. Is a trapezoid less than a midpoint? Might be, we don't know. These are both increasing, right? Both these graphs are increasing, like they said. Here the trapezoid is over, here the trapezoid is under, because it depends on concave. Okay? All right, see, so make sure, again, when you're, you know, nobody was asking about those, and you could have looked up the odds. But even when you're doing them, if you weren't totally sure, I mean, you should be asking about that stuff. Okay? 51. Now, 51 talks about this thing called the divide and conquer strategy. So, Max, graph sine of x squared for us, and do a zoom fit from 0 to 2. So, do sine of x squared. Now, there was an example back in your book. So, if you really wanted to know how to do 52 badly enough, you could have, if you'd have looked back at one of the examples in the book, and I did that on purpose. I left that for you to see if you could look at it. Go 0 to 2, go to Windows settings. Okay, so yeah, let's talk about this. This is a zoom fit. We talked about it way back earlier in the year, but it really becomes handy in integral problems. Because if we want to draw a graph, and almost always in a definite integral, we're looking at integral from, like this one, 0 to 2. So the best way to do it is, let's go back to it. So we haven't done the zoom fit yet. So we go to our Windows settings. So go to our window. So if we're looking at integral from 0 to 2, I only want to see that graph from 0 to 2. So we go to Windows settings. We set our x, min, and max 0 to 2. Okay, that's good. You got that. Hit OK. And then we go back to menu. Go back to window. We go to zoom fit, which is the A. And it fits our y values for us. So we put in our x, min, and max. And then we do zoom fit to see the rest of the graph. Okay, now, it says, use divide and conquer, or how can divide and conquer be used with midpoint trapezoid approximating sums to trap I, to trap it. Well, what do we mean by trap it? We mean, let's find an under approximation and an over approximation. Let's find a number we know is below the actual answer and one that's above, because this is one of those integrals we can't do the antiderivative, we don't know the exact area. Okay, they said midpoint and trapezoid. Well, what determines whether a midpoint or a trapezoid is going to be over or under? Concavity. Okay, now let's first talk about left and right. Let's say this problem said something about left and right. How do we know when left and rights are over and under? Increasing, decreasing. So where does this one change from increasing, decreasing? Right here. So if we could find this point, and let's say it's, well, Max, I know you could, so why don't you do it real quick? Why don't you just go trace, menu, trace, and let's trace until we get up to that max. There it is right there. What's that? Here. 1.25, I think. 1.26. Okay, go to your settings here. Go to menu, settings. I think we can take off float 3 and do float. I don't know why you're float. After we updated, did it? Okay, maybe it did that in every, so maybe everybody needs to do that. Okay, so go to right arrow, just right arrow, just right arrow. Go to float, hit enter a couple times. Yeah, hit enter again, make default. Hit enter. Okay, 1.253, okay. So, at this, oops. Okay, right there. All right, so right here at 1.253, right, we've got our match. So, if we did the integral, right, from 0 to 1.253, and then we did the integral from 1.253 to 2, right, what would we know would be less than this answer?
Left, right,
Lefts, right? Let's just talk about lefts and rights right now. Lefts. So F, L, whatever, some L. It just said explain how you could use it. So some number of lefts would be under and rights would be over, right? Now what about this integral? The opposite. Rights would be under, right, over here. Right rectangles would be under and lefts would be over. So we could take, so from here to here, so if we took these, if we did this, say we did 10 of them or whatever, it doesn't matter. So whatever this approximation was here, and we add that to that approximation, so we do 10 lefts, let's say, plus 10 rights, and we add that together, that would be an under approximation, right? And then if we took these rights and added it with these lefts, that would give us an over approximation of the 0 to 2. See how that's divide and conquer, right? We divide it up into pieces where we know it's increasing and then where we know it's decreasing. And then do lefts for under, here do rights for under, add that up. So we would track the actual answer. We would know that the actual answer has to be somewhere in between, right? So it's just a strategy of saying, okay, we don't know how to do the antiderivative. How could we do something that we know would be? Because if I just did 0 to 2 and did a left, how do I know if it's over or under, right? I don't know for sure. Now, it's going to be one or the other. It's going to be over or under. But I wouldn't know for sure which one it is. Now, if I did a left and did a right, and then I'd be able to tell. But this is just how we can know for sure. Okay, this is under and this is over because we can break it up into increasing, decreasing. So now to number 51. How could we use trapezoids and midpoints to break it up? So we find what? The inflection point, right? So it looks like it's concave up. I'm just going to guess. Looks like it's concave up until about here. And then it looks like it's concave down the rest of the time, but I actually think it switches concavity in here somewhere. So I think if we were going to find inflection points, I think there'd actually be a couple of them there, right? And we don't need to bother. But so explain how you would use divide and conquer strategy. You would find the inflection points and divide it up into pieces that were concave up and concave down. So what would be under this part? We'll do the unders in red. What would be under here? Remember, midpoints are tangent, right? So a midpoint would be this tangent trapezoid, like that, right? So those are going to be under. So midpoints would be under, and then we would add in this section, what would be under here? Trapezoids, right? A trapezoid would go under, right? And so we'd add some trapezoids there, and then this last section, midpoints again. So we would do some midpoints in the first section, we do some trapezoids in the next section, we do some midpoints in the next section, and that would give us an under approximation. And then the reverse of that to get our over. To get our over approximation, we do trapezoids in the first section, because this would be, our trapezoid would look like this. We do trapezoids in the first section, we do midpoints in the next section, we do trapezoids in the last section, add those up, and then that would give us an over approximation. Okay? And we would trap the interval. That's called divide and conquer, trapping the interval. Okay, all right. So let's move on. We're going to kind of stick with this same theme today, but we are going to, you will talk a little more about this idea of max error. So in our notes, we can do this. I'm also going to send you document here because I think some of today's homework is going to ask you about doing 20 rectangles or even 10. If it says 10, we're going to use this. We're not going to calculate it by hand. So today's homework is going to be more about using this calculator program I'm going to give you to just calc. So if it wants 10 midpoints, if it wants 20 midpoints, if it wants 50 trapezoids, we're going to just type it into this little calculator program I've got, okay? So here's our little formula. Now, I changed it a little bit from yesterday. Yesterday we said that this was equal to our amount of error. So now we're going to talk about an inequality. So if I give you a problem where I say this, right? I say the I minus T sub n is less than or equal to 0.05. I'm saying, okay, this is the amount of error. That's what we talked about yesterday, right? Take the exact answer minus the approximation. That's the amount of error. If I want that to be less than or equal to 0.05, what I'm saying is I want my amount of error to be no bigger than this. I just call that my max error, right? So this number in the box is my max error. That's the most I want this to be off. So the idea, what we're going to lead towards, we're going to do this tomorrow. What we're going to do tomorrow is we're going to figure out how many rectangles, or in this case, how many trapezoids would it take where I know I would be off no more than that. Remember what I said yesterday is the thing we're trying to get is how does a calculator know it's got 12 decimal places of accuracy? How does it know it? If it doesn't know the exact answer, that's what we're going to get to tomorrow. Okay, so if I want my max error to be this, that means I've got at least 2 decimal places of accuracy. Now, I might have more. That's going to be the thing. That's how the calculator does it. How does it know it's got 12 decimal places of accuracy if it doesn't know the exact answer? Well, the way it's going to know it is going to know the max error. This is the most we can be off. We're probably closer. So if my max error is 0.05, my actual error might be less than that, right? My actual error might be less than 0.05, so I might have 3 decimal places or 4 decimal place accuracy, but I know for sure I got 2. Okay, that's what we're going to be getting into. But this is what the notation will look like. So when you see this is your max error. Now, if you go back to algebra, you might have some problems in homework that say something right an error bound. Well, an error bound just means if my max error is 0.05, it might be under 0.05 or it might be over 0.05, right? So all we do, so if we take off the bars, you might remember from algebra class, this would be like, okay, this would be 0.05 and this would be negative 0.05, right? And then if we add T sub n to both sides, what we get is this. We just get, okay, my actual approximation is somewhere in between my trapezoid minus 0.05 or my trapezoid plus 0.05. Doesn't that make sense? Okay, so if I take my approximation, and I know the most it's off is 0.05, then, right? So if you take my trapezoid, if I add 0.05 on, or I take away 0.05, I know the exact answer has to be in there somewhere. Okay, because the most the trapezoid is off is 0.05. Okay, so if it's over by 0.05, I take off 0.05, right? Or if I add on. So that's all that notation is. That's just some algebra notation with error bounds and so forth. Okay, so that's just something you want to know about. All right, let me give you the document, and then we're going to talk about something that's going to be on Friday, because I don't know. Does anybody know they're not going to be here tomorrow? Friday? Okay. Well, Friday's going to be work time, so you'll just have to, it's going to be work time on this project, graphic project we have, which we're going to talk about, so you'll just have to do that on your own. So we work time on that, but also packets and stuff like that. So anyway, tomorrow we're going to go into section 2. We're going to learn about these max errors, how we calculate them, and all that stuff. So if you're not here, you have to watch the video, I guess. But anyway, so where was I? Oh yeah, I was going to give you this calculator. Okay, so
Is that like a drawn out project?
kind of. Yeah, this is what you guys are going to be working. This is not the greatest example, but it's not bad. It's the only one left from the old school. I left all of my other ones at the old school. This is actually Mr. Talmadge's. I'm going to tell you about it here in a second. Okay, but If you want some bonus points, you add some color or whatever. He might have got a bonus point or two. I don't know. Most people for bonus points put it on a big poster board or something, bigger poster board, not real big. But anyway, so this little program here called Area, I'm going to send that to you. So let's just, okay, you should be getting that. Okay, now wait, now don't, what you want to hit here is you want to hit, just hit OK. Just hit OK. Just choose OK on that. Okay? All right, now, what we want to do, it says we want to put this file in the My Library folder. MyLib sits for My Library. So go to, so actually we do want to open it up. So go ahead and go to your documents, or go to your home screen, I guess. Go to My Documents. Go to your page. I can't help. Okay, and open it up so you're on this page right here. I guess. So I guess I can just hit open. So go to this first area. Yeah, it's called Area, and then just it says, do you want to save changes? Don't worry about that. Save. Yeah, so just, okay, so now let's do what it says. So go to Doc, File, Save As, and you want to put it in the My Library folder. Did you want to save that? Are you on the Save As part?
Yeah.
Okay. That's not good. Yeah, I don't know. You don't? No. Okay, hold on. Let's do this. So, go to your, open up the area. Open up area. Area.
So we hit save.
Oh, I found it.
Where is it?
You have to hit the thing in the top right hand corner that says open folder. It's on the left side of the two folders.
New
Is
folder,
this
folder
folder
up.
Folder up, and then click
Okay, so you go File,
4 down.
Save As,
Four down, three.
No, this is my left.
and then you go,
You see it?
yeah,
I
this,
have it.
Tab up there.
yeah, do you arrow up?
I hit save.
Hit
Yeah.
arrow up. Yeah.
Then we go.
Oh, do you have to just scroll with your thumb to get up there?
Yeah.
So which one, the
The one that says like folder there. Yeah.
folder up? Yeah, there you go. You could click on that little down arrow, that AP count block.
No, it's not in.
Okay, hit it.
There's like 3 things shaded here.
Okay, now go to the Dock button and it says you have to refresh the library. So where it says go to Dock and then refresh libraries, number 6. Okay, anybody else have trouble? Did everybody get it with the folder up?
You want to start area?
Shannon, did you get that? Did that work? Everybody? Yeah, so now,
We are in it already. That's just-
yeah, you're in it. So if you're on this page, okay, now go to, go to the next page where it says RAM. This is the page you'll pretty much stay on. Now, RAM stands for Riemann Approximation Methods. Now, technically, it's not Riemann or rectangles because trapezoid and Simpson are in there too. And trapezoid and Simpson are not rectangles, remember, okay? But anyway, that's fine. So hit enter, and what this is doing is running this program. So if you ever, usually you can just keep hitting it. Every time you come to this page, you can hit enter. So if you hit enter, and oh, this is not, I guess Max is not here. If you hit enter, it comes up to this, right? So anytime we have 10 or more And probably not going to even ask you to do it on the quiz. There might be one, but probably not. But in the homework, anytime there's 10 or 20 or 50 or whatever, you go to this thing. You open up this area document, and you go to this page where it says RAM. You might have to just type RAM parentheses, right? If you delete it, if you happen to delete that command, but just type RAM parentheses. It should go bold, and it should run. Is everybody's running? Everybody's working? Okay. Now hit OK. Okay, or enter. How many decimal places? Let's say we want to do 3. That's fine. Okay, we'll hit OK. Now, what function do we want? So let's do that one we did yesterday, which was just x squared. Now we could go in the graph screen, store it in F1, but usually we can just type it right here. So let's type x squared. Hit enter. And yesterday we did it from 0 to 2, I think. So hit OK. 0. Oh, 2's already in there. Is that in yours too? Okay, but you can type something else in if you want. And then how many subintervals? We did 3. Remember we did an L3 and R3, right? So let's type in 3, hit enter. Now we get an error message. It says Simpsons isn't going to work because it's odd. That's fine. It's okay. We did S6 when we did Simpsons, I think, yesterday. But let's hit OK. And there, remember those numbers, 1.481, 4.148, remember we worked those out? 2.593 was a midpoint, 2.815 is a trapezoid. Now it gave us a Simpsons. I'm not sure how it did that or what it did. It probably tried, but but of course we knew it was exact, and that's what we did get. But we could do, I don't think it did an S6, no. If we hit enter, and we just hit enter again, when I'm on a page I could retype RAM, but remember when you hit enter, it just redoes the last thing you did, which was to run that. So we can hit enter and go 3 decimal places. It doesn't say, that's too bad, it didn't say what I had. X squared, 0, 2. It did say the 3 subintervals, so that's weird. And then let's change that to 6. And then we can do 6 subintervals, and then of course there's our Simpsons. Of course that changed our left and our right and everything. But they're all right there. And then if you hit OK and it goes away, they are saved here. They are here, right? Here's the ones we just did, and so they are on your, they are in that screen. It's just a calculator page. All it is. Okay. Now for you guys that were in computer programming, if you're interested, if you go over here to the next, it talks about this. Now it talks about some other programs that are in this file, but we can't get to them. But it says RS. Well, let me see. They're listed over here. They're little functions that are written. RS was just a Riemann sum. Gives left, right, midpoint, Riemann, trapezoid, Simpson, the exact. So you can actually just type RS. But then you have to have your function stored in F1 on the graph stream. And then you can just type these little functions in, put your A and your B and your N right in there. Although the B and A, you put them in backwards. And then the N. And that's a Riemann sum. RS, if we keep going down, RS is just, come on, why is that not going? Is yours scrolling now? Oh, it must have to go to the next page. So RSL, just the Riemann sum left. I never use these. I mean, this is just if you want to mess around with it, so I never use these. What I wanted to take you to, so 1.7 is another calculator page that has RAM on it, so you can do that. So 1.2 or 1.7, whatever those pages are, you can do those. And then 1.8, no, 1.9, I guess. Here's the actual program. Here's the actual RAM program. Now, you want to be real careful in here that you don't go in and mess around with it, right? And I suppose if you go around and mess around with it, and then as long as you don't save it, if you close out of it, don't save it, and then open it back up, you're probably fine. But if you scroll down here, you know, you can see kind of some commands. These are some mode commands, but like a text command is going to print something on the screen. It sets the D, the number of subdivisions, or the number of decimal places to 3 right away. You notice when we said how many decimal places, it had a 3 in there already. And then this is the define box where it says f of x equals. It's just going to let f of x equal whatever's in F1 if you want to do it that way, or you can just type your own in. Here's where you get it. The request command is where that box comes up and lets you type stuff in. So whatever you type in is going to go into A, into B, it's going to go into N. And then you got some if statements here. And it says if text is odd, Simpsons won't work. Else, end if, you can see some of this. It uses the sigma commands. So to do the left rectangles, notice it's I minus 1. It starts I at 1. We know lefts usually start at 0, but they went ahead and just put an I minus 1 in here. So it's f of the left starting edge plus, and of course I minus 1 would be 0, so this would be a plus 0h. Well, that's going to be a, the left edge, and then I will increment, and then h it defines to be the width. H is b minus a over n, right? So that's like your delta x. And here's your right rectangle, so you can see pretty quickly. Here's your midpoints. Notice they take off 0.5, so that takes off half the interval, and so that gives you your midpoint. Here's your trapezoid. You can kind of see the f of a plus I minus 1 f of a. So it gets those, and then it does Simpsons in here. You can see your 4. You can't see the rest of it there, but anyway. So it just sets those up as sigmas. Just sets those up as sigmas and does them, and it runs how whatever you put for n, it does that many of them. So you can see it was not horribly difficult to program, especially if you can do sigma notation. And then the exact answer, they just do an integral, and then they give out the answers, and that's what the rest of the section. So anyway, if you want to see what that looks like. But so when we talk about using your calculator program, when I say use your calculator program to do your S50, right? You can just run this. So if I hit enter, let's do it one more time. So if I do, let's say we do 3 decimal places, and I want to use my x squared, and I want to do, oops, and I want to go 0 to 2, and I want to do 100 subdivisions. Boom, just like that. Look how accurate it is, right? So if you do lefts or rights with 100 of them, you get a pretty good approximation. All right. Enough of that. Got to show you something here for this assignment we're going to do we're going to work on Friday. This is going to be due next week. This is going to be due on Thursday, our last day before spring break. We used to go, the AP biology class used to go up to the Niobrara River. We used to go up in September over Labor Day weekend. Yeah, not anymore. You guys have to do the fast. But this is years ago. I don't. We haven't done it for 10 years. Mr. Talbot and I would go up there with the AP biology class because they up at the Niobrara Preserve. And did he talk about this in class? You weren't in class. But go up there and spent 3 days and over Labor Day weekend, and we did they did a bunch of different scientific experiments, but I got involved a few years after we both came here, and we started talking about connecting the math, some math with it, some of the different math parts, because there were some math things that were involved that he asked my help on. And so we started talking about it. We said, well, we should, some of those kids are in Calc and that class, so maybe we should try to come up with some different things. One of the things we did was measuring flow rate of the river, because that had a scientific aspect. That the Niobrara is a very wide, shallow, slow-moving river, and it's great for canoeing, and people go up there and canoe and tube on it and stuff like that. And so you compare a river like that with a more narrow, deep, fast-flowing river, there's going to be a lot of different types of aquatic life and a lot of different organisms, a lot of different plant life that's going to live in one of those ecosystems versus another, right? And so one of the things we wanted to measure, one of the things biologists are interested in a system like that would be the flow rate, how much water is flowing past a certain point at a certain time. So what we did is we see the string right here. You can see we took a string and we marked it off in 1 meter increments with a little black marker, and we tied it between 2 posts. And we just went across, we started at the bank, and we stretched it out into the river as far as, we could. And then every meter, we took a measurement. We had this wooden stick here, and it was marked off in 10-centimeter increments. Okay? And so we would just put that in the water, and we would read right at the water level where it was. So if it was between 20 and 30, we'd estimate. Okay, that's about 24, right? We'd write that down. She's recording. So at 1 meter, 2 meters, 3 meters, we took all these depth measurements. Okay, so we got all these depth measurements as we went across the river. Okay, so what did we do with that? Well, we took those depth measurements and somewhere. Are you in that class? So he's never talked about the Niobrara trip?
He always,
Really likes stars.
he's never said we were playing.
Well, you'll have to ask him. We were just talking about it.
Smith Falls, they have like a lot of.
How far is it from?
Oh, here it is right here. All right,
Okay.
so what we have on here is the data. This is from 2001, I believe. And so what you have is the left hand, so you have your X and your Y, right? The X column is the meters, that's the depth, that's going across. 0 meters would be at the bank, 0, 1, 2, 3. It was 144 meters across, okay, wide. It's a very, very wide, very, very wide river, okay? And then the centimeters, so you're gonna have to get those units to agree, in which you can just do easily in your calculation. And then you got centimeters, right, the depth, okay? On the back, you've got, because coming into the Niobrara are all these little feeder streams. So we took this little stream, and the stream's only about this wide. You can see it's about 80 centimeters, so it's only about a meter wide. So this little stream was going through there, and we took measurements there too, okay? So your job is going to be able to graph all these points, all 144 points, okay? But we're going to make our width of our rectangles 2. Okay, now we're going to do that so you don't have to draw 144 rectangles. We don't have hardly enough room on the graph paper. So you only have to draw 72 rectangles. Okay, we're also going to make a width of 2 because then the people doing the midpoint ones, and see, you're going to do left rectangles, you two. You're doing your own project, but you're going to draw left rectangles in yours. You're going to draw left rectangles in yours. Okay, you guys are going to draw midpoint rectangles, and you guys are going to draw right rectangles. Okay. So again, you're doing your own thing. It's your own project, but you're going to have different rectangles. Okay, so this person had left rectangles, looks like. So they had their first point, do their left rectangle. But the first thing you do is just plot all the points. So on the graph paper, so everybody will need at least.
Wait, do you want us to make them in meters or in centimeters?
I would do meters going across, and I would do centimeters going up and down. And then you can adjust for that in your calculation.
So you want to
Makes
graph
sense.
it as meters and
Wait, I
centimeters.
don't argue.
Okay, listen. So this is his stream. Now I would suggest you're going to have too many points. He fit it on 2 pieces of paper, but this was a different year's data. This only had a 116 meter wide strip. So you're going to need 2 pieces of paper, probably put together like this, to fit in 72. So what I would want you to do is you would want to start over here, 0, 2, 4, 6, 8, right? You're going to want to go by 2s across here is the only way you're going to fit 144 on here. Does that make sense? So you're going to go by 2s across, and then probably going up here by 5s, I'm guessing, 4s or 5s. You have to see what the biggest Y value is. I see something in the 50s, 62, looks like 62 or so is the biggest. 75, so you want to fit 75 going this way. So count how many there are. I think if you go by 3s or 4s, you can probably fit, right? You can go by 3s or 4s going up here. That'd be centimeters. And then go by 2s across here. Okay, now, you're still going to plot all of them though. So you'll plot 0, you'll plot 1, but you'll be in between a line, right? So if I look at this right here, so if I pull this, and we'll talk about this more on Friday when you're doing it, but if you're not going to be here, obviously that's going to be, okay? So if I look at this, if I look at my grid, so if I look at my grid, these would be like your blue lines on your paper here, okay? So this would be 0, this would be 2, this would be 4, this would be 6, this would be 8. So you would plot 0, what's the first one? 0 what? 0, 0. And then what's 1? 1, 5. So let's say we went 5, 10 like this, so you would go 1, 5. and then you go 215 would be here, right? You're going to plot every point, and then you're going to connect it with a nice, smooth, right, kind of thing, whatever. And so, your graph will look whatever, like this, right? Now, if you're a left rectangle person, who's the left? You guys? If you're a left rectangle person, your first rectangle will be here, right? If you're a midpoint rectangle person, your rectangle will be here. Does that make sense? And if you're a right rectangle person, your rectangle will be here. Make sense? So everybody's plotting all the points.
But we only plot every 2 rectangles.
But rectangles are going to be too wide, so your rectangles will be the same width as your blue lines, right? So left rectangle, midpoint rectangle, right? So your rectangles are going to be a width of 2. So you're only going to have 72 rectangles. On the third piece of graph paper, then, you would do your string, right? Now that'll fit easily because you don't have very many points, so you can make that nice and big. He didn't make his very big. Most people just use 2 pieces for the river. You'll need it for yours, and then a third piece for that. Now, so if you want to, for some bonus points, right, put it on some nice poster board. If you just want to draw the graphs with the rectangles, no color, and then you do have to do the calculation. Now, you can certainly do dot, dot, dot. So notice you've got B minus A over N, F of, dot, 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 F of, right? And then do the calculation for the area. We'll talk more about the area tomorrow, the calculation or whatever, but that's the project. That's going to be due next Thursday. I'm going to give you time to work on Friday so you can be plotting all your points and drawing your rectangles and stuff like that. You can work on that on Friday. Okay?
Just leave it on the desk a second.